One of the most confusing things about learning basic particle physics is mastering all of the particle names. I mean, you have fermions, bosons, baryons, mesons, leptons, and on and on and on. It's really quite bewildering. So in this video, I thought I'd try to help you sort it all out. To begin with, there are two types of names. There are the names that are specific types of particles, like the electron, proton, or neutron. Then there are the names which are the classes of particles, ones that distinguish between different kinds of spins, the forces the particles feel, and the kinds and types of particles found inside them. To make things even more complicated, some of the names were picked in the 1940s or something, and the names are historical, meaning that back in the day, the particles were classified into categories that made sense then, but don't anymore. So let's talk about some of the obvious ways in which particles can be characterized. They can be characterized by mass into categories that are small, medium, and large. They can be categorized into different kinds of spin, say having spins that are either an integer or half-integer multiple of the fundamental unit of spin. That just means that particles can have spins of 0, 1, 2, and things like that, or a half, 3 halves, 5 halves, and so on. Then there's electrical charge, with particles having either electrical charge or being neutral. It turns out that there isn't a special word distinguishing between the two, which is weird, but, well, that's the way it is. And then one can classify the particles as feeling the strong force or not. This was also historically important. So those are the biggies. Now let's dig into the names. We'll start with an obsolete set of categories. You'd think it'd be silly to talk about an obsolete category, but they have historical significance and can cause modern confusion, so I'm going to do that. So let's think about the 1940s and 1950s. At that time, it seemed to make great sense to classify particles in terms of their mass. Scientists kind of base the names with the proton and neutron as being the standard. Protons and neutrons have about the same mass, so, well, that kind of makes sense. There were the very light electrons and neutrinos with masses no bigger than 0.05% the mass of the proton. Because this was so small, these particles were called leptons, for the Greek word leptos, which means fine or small or thin. That seemed like a great name for light particles. In contrast, there were particles that were the mass of the proton or maybe twice as heavy. Because these were the giants of the particle world, they were called baryons, for the Greek word baris, for heavy. Again, a sensible name. Finally, there were particles that had a mass somewhere between the leptons and the baryons. Their masses were in the range of about 10% that of the proton to about half of a proton. These particles were called mesons, from the Greek word mesos, which means intermediate. Briefly, the word mesotron was used, but, well, that didn't last very long. Now, this mass-based classification makes sense, but it turns out to be a false lead. Baryons feel the strong force, while leptons do not. Most of the mesons also feel the strong force, but there was an outlier called the muon. It was a low-mass meson, but it didn't feel the strong force. That ended up being a powerful clue in the proper way to classify particles. This strong force classification ended up being important. There was a name for particles that felt the strong force. They were called hadrons. This word actually was invented pretty late. Physicist Lev Ocon coined it in 1962, and it comes from the Greek word adros, which also means heavy. On the spin side, there were the particles with integer spin, which were called bosons after Satyendra Nath Bose, who developed the mathematics describing how they behaved and worked with Einstein to get it published. And then there were the fermions. Fermions are particles with half-integer spin and were named after Enrico Fermi, who, along with Paul Dirac, pioneered the mathematics that describe them. The heavy baryons and the light leptons were all fermions, while most of the middleweight mesons were integer spin bosons. However, the muon was a fermion, which was another clue that the muon didn't fit into the historical and mass-based lepton, meson, and baryon classifications. It was in the 1960s that Marie Gilman and George Zweig independently came up with a key insight that made it possible to clarify the whole thing. They realized that all of the baryons and most of the mesons were made of smaller particles that we now call quarks. Quarks are fermions with spin a half, although because the spins can point in one direction or the opposite, they can have spins of plus a half or minus a half. Quarks feel the strong force, and since the muon didn't feel the strong force, it was clear that it actually belonged in the lepton category, not the meson one. It also meant that the muon didn't have quarks inside it. So now we're ready for the proper way of characterizing particles. The spins of particles are properly separated into the spin half fermions and the integer spin bosons. Leptons contain no quarks and hadrons do. The mesons and baryons are both hadrons. Mesons contain a quark and an antimatter quark, while baryons contain 3 quarks. Since quarks are fermions with spin a half or minus a half, you can see how they explain the spin of the mesons and baryons. Take 2 particles with the spin of plus half and minus a half, and they have to add up to an integer spin, either minus 1, 0, or 1. That's why mesons are integer spin bosons. Now take quarks 3 at a time, and you have to have half integer spin particles with spins of minus 3 halves, minus a half, plus a half, or plus 3 halves. That's why baryons are spin half fermions. Leptons aren't thought to contain smaller particles within them. Leptons are kind of like quarks, but without feeling the strong force. So leptons are fermions. The diagram you see here is kind of a Venn diagram of particles. There are the distinct fermion and boson classes. Within those classes, some particles feel the strong force and some don't. What makes them feel the strong force is they carry quarks. There are bosons which don't carry quarks. They are the photon, the W and Z bosons, the gluon, and the Higgs boson. All of them are particles that cause forces to happen. The known forces are the strong force, the weak force, electromagnetism, and gravity. These bosons that aren't hadrons are responsible for these forces. There is one force-causing boson that hasn't been discovered, and that's called the graviton, which is thought to be responsible for gravity. I predicted it will be millennia before we find direct evidence for gravitons. So that's it. That's how particles are characterized. All the other names, things like electrons, protons, neutrons, neutrinos, pions, kaons, delta particles, japes, etc., can all be classified by this basic diagram. It's also probably important to remember that these particles I just mentioned are all examples of specific particles, not general ones. For example, there's only one type of electron. And even the less familiar particles like the muon and pion are contractions of mu lepton and pi meson. Keeping separate in your mind the specific particles and general ones is key to understanding this whole subject. For those of you who are adventurous, I've posted a flowchart in the description of the video that helps you classify any subatomic particle you discover. And if you find a particle that the flowchart doesn't describe, let me be the first one to congratulate you on your upcoming trip to Stockholm.